Rollups are all the rage in the Ethereum community and are poised to be the key scalability solution for Ethereum for the foreseeable future. But what exactly is this technology? What can you expect from it? And how will you be able to use it? Welcome back to Ethereum Audible, Ethereum in Depth. I'm Yoshua Zlatogorsky, and welcome to our complete episode, complete guide to Rollups, which is what we are going to be diving into today. Over the past two episodes, we've been diving into the Ethereum merge and the shift to Ethereum 2.0. Last week, we dove into the shift from a sharding-centric roadmap to a rollup-centric roadmap. And today I want to be diving into a primer on the different kind of layer 2 scaling solutions that are out there. Channels, plasma, and rollups. And we're going to be doing that with a piece that Vitalik wrote in January of 2021 called An Incomplete Guide to Rollups. Now, there are a few other really good resources on rollups, and I'm going to link to them in the podcast notes, but this is a really good primer to start with. But first, I want to thank the sponsors of this show who made this episode possible. This episode is brought to you by Alpe Audio. Want to learn on the go but need more depth than a podcast? Alpe is the app for you. It's an audio education app that brings great in-depth courses that are as fun as podcasts but as educational as a degree. Each lesson comes with summaries, additional resources, flashcards, and more. You can even find Ethereum Audible on Alpe with all of those additional resources. If you want to check it out, head over to get.alpeaudio.com, and that's A-L-P-E, Alpe, A-L-P-E. Let's go. An Incomplete Guide to Rollups by Vitalik Buterin. Rollups are all the rage in the Ethereum community and are poised to be the key scalability solution for Ethereum for the foreseeable future. But what exactly is this technology? What can you expect from it? And how will you be able to use it? This post will attempt to answer some of those key questions. Background. What is Layer 1 and Layer 2 scaling? There are two ways to scale a blockchain ecosystem. First, you can make the blockchain itself have a higher transaction capacity. The main challenge with this technique is that blockchains with bigger blocks are inherently more difficult to verify and likely to become more centralized. To avoid such risks, developers can either increase the efficiency of a client software or more sustainably use techniques such as sharding to allow the work of building and verifying the chain to be split up across many nodes. The effort known as ETH2 is currently building this upgrade to Ethereum. Second, you can change the way that you use the blockchain. Instead of putting all activity on the blockchain directly, users perform the bulk of their activity off-chain in a Layer 2 protocol. There is a smart contract on-chain, which only has two tasks: processing deposits and withdrawals, and verifying proofs that everything happening off-chain is following the rules. There are multiple ways to do these proofs, but they all share the property that verifying the proof on-chain is much cheaper than doing the original computation off-chain. And just side note here, Yoshua, I think that's a mistake. I think Vitalik meant to write on-chain because the sentence makes much more sense as there are multiple ways to do these proofs, but they all share the property that verifying the proofs on-chain is much cheaper than doing the original computation on-chain. And to my editing of Vitalik's post. State channels versus plasma versus rollups. The three major types of Layer 2 scaling are state channels, plasma, and rollups. They are three different paradigms with different strengths and weaknesses, and at this point we are fairly confident that all Layer 2 scaling falls into roughly these three categories, though naming controversies exist at the edges, for example, Validium. How do channels work? Imagine that Alice is offering an internet connection to Bob in exchange for Bob paying her 1/10 of a cent per megabyte. Instead of making a transaction for each payment, Alice and Bob use the following Layer 2 scheme. First, Bob puts $1 or some ETH or stablecoin equivalent into a smart contract. To make his first payment to Alice, Bob signs a ticket which is basically an off-chain message that simply says 1/1000th of a cent and sends it to Alice. To make his second payment, Bob would sign another ticket that says 2/1000ths of a cent and send it to Alice, and so on and so forth for as many payments as needed. When Alice and Bob are done transacting, Alice can publish the highest value ticket to chain, wrapped in another signature from herself. The smart contract verifies Alice and Bob's signatures, pays Alice the amount on Bob's ticket, and returns the rest to Bob. If Alice is unwilling to close the channel due to malice or some technical failure, Bob can initiate a withdrawal period, for example 7 days. If Alice does not provide a ticket within that time, then Bob gets all his money back. This technique is powerful. It can be adjusted to handle bidirectional payments, smart contract relationships, for example if Alice and Bob are making a financial contract inside of the channel, and composition. If Alice and Bob have an open channel and so do Bob and Charlie, Alice can trustlessly interact with Charlie. But there are limits to what channels can do. Channels cannot be used to send funds off-chain to people who are not yet participants, and channels cannot be used to represent objects that do not have a clear logical owner, for example, something like Uniswap. And channels, especially if used to do things more complex than simple recurring payments, require a large amount of capital to be locked up. How does Plasma work? To deposit an asset, a user sends it to the smart contract managing the Plasma chain. The Plasma chain assigns that asset a new unique ID. Each Plasma chain has an operator. This could be a centralized actor or a multisig, or something more complex, like a proof-of-stake chain or a designated proof-of-stake. Every interval, which could be 15 seconds, an hour, anything in between, the operator generates a batch consisting of all the Plasma transactions they have received off-chain. They generate a Merkle tree, where at each index X in the tree, there is a transaction transferring asset of the same ID that we assigned in the beginning, if such a transaction exists, and otherwise that leaf is 0. They publish the Merkle root of this tree to the chain. They also send the Merkle branch of each index X to the current owner of that asset. To withdraw an asset, a user publishes the Merkle branch of the most recent transaction, sending the asset to them. The contract starts a challenge period, during which anyone can try to use other Merkle branches to invalidate the exit by providing that either 1. The sender did not own the asset at the time that they sent it, or 2. They sent the asset to someone else at some later point in time. If no one proves that the exit is fraudulent for, say, 7 days, the user can withdraw the asset. Plasma provides stronger properties than channels. You can send assets to participants who were never part of the system, and the capital requirements are much lower. But it comes at a cost. Channel requires no data whatsoever to go on-chain during normal operation. But Plasma requires each chain to publish one hash at regular intervals. Additionally, Plasma transfers are not instant. You have to wait for the interval to end and for the block to be published. Additionally, Plasma and channels share a key weakness in common. The game theory behind why they are secure relies on the idea that each object controlled by both systems has some logical owner. If that owner does not care about their asset, then an invalid outcome involving that asset may result. This is okay for many applications, but it is a deal breaker for many others. For example, Uniswap. Even systems where the state of an object can be changed without the owner's consent, say an account-based system where you can increase someone's balance without their consent, do not work well with Plasma. This all means that a large amount of application-specific reasoning is required in any realistic Plasma or channel deployment, and it is not possible to make a Plasma or channel system that just simulates the full Ethereum environment, or the EVM. To get around this problem, we get to Rollups. Rollups. Plasma and channels are full layer 2 schemes, in that they try to move both data and computation off-chain. However, fundamental game theory issues around data availability means that it is impossible to safely do this for all applications. Plasma and channels get around this by relying on an explicit notion of owners, but this prevents them from being fully general. Rollups, on the other hand, are a hybrid layer 2 scheme. Rollups move computation and state storage off-chain, but keep some data per transaction on-chain. To improve efficiency, they use a whole host of fancy compression tricks to replace data with computation wherever possible. The result is a system where scalability is still limited by the data bandwidth of the underlying blockchain, but at a very favorable ratio. Whereas an Ethereum base layer ERC20 token transfer costs 4,500 gas, an ERC20 token transfer in a rollup takes up 16 bytes of on-chain space and costs under 300 gas. The fact that data is on-chain is key. Putting data on-chain and having consensus on that fact allows anyone to locally process all the operations in the rollup if they wish to, allowing them to detect fraud, initiate withdrawals, or personally start producing transaction batches. The lack of data availability issue means that a malicious or offline operator can do even less harm. For example, they cannot cause a 1-week delay, opening up a much larger design space for who has the right to publish batches and making rollups vastly easier to reason about. And most importantly, the lack of data availability issues means that there is no longer any need to map assets to owners, leading to the key reason why the Ethereum community is so much more excited about rollups than previous forms of layer 2 scaling. Rollups are fully general purpose, and one can even run an EVM inside a rollup, allowing existing Ethereum applications to migrate to rollups with almost no need to write any new code. Okay, so how exactly does a rollup work? There is a smart contract on-chain which maintains a state root, the Merkle root of the state of the rollup, meaning the account balances, contract code, etc. that are all inside the rollup. Anyone can publish a batch, i.e. a collection of transactions in a highly compressed form together with the previous state root and the new state root, which is the Merkle root after processing the transaction. The contract checks that the previous state root in which the batch matches its current state root. If it does, it switches the state root to the new state root. To support depositing and withdrawing, we add the ability to have transactions whose input or output is outside the rollup state. If a batch has inputs from the outside, the transaction submitting the batch needs to also transfer these assets to the rollup contract. If a batch has outputs to the outside, then upon processing the batch, the smart contract initiates those withdrawals. And that's it, except for one major detail. How do we know that the post-state roots in the batches are correct? If someone can submit a batch with any post-state root with no consequences, they could just transfer all the coins inside the rollup to themselves. This question is key because there are two very different families of solutions to the problem, and these two families of solutions lead to the two flavors of rollups: optimistic rollups versus ZK or zero-knowledge rollups. The two types of rollups are 1. Optimistic rollups, which use fraud proofs, as in the rollup contract keeps track of its entire history of state roots and the hashes of each batch. If anyone discovers that one batch had an incorrect post-state root, they can publish a proof to chain, proving that the batch was computed incorrectly. The contract verifies the proof and reverts that batch and all batches after it. 2. ZK rollups, which use validity proofs. Every batch includes a cryptographic proof called a ZK snark, for example, using the Plonk protocol, which proves that the post-state root is the correct result of executing the batch. No matter how large the computation, the proof can be very quickly verified on-chain. There are complex trade-offs between the two flavors of rollups, and we'll run through a few of them. For the fixed gas cost per batch, in an optimistic rollup, we're looking at 40,000 fixed gas costs per batch, and that would be a lightweight transaction that mainly just changes the root value. In a ZK rollup, it'll be around 500,000, which is the verification of a ZK snark is quite computationally intensive. Withdrawal period for an optimistic rollup is usually around 1 week, because withdrawals need to be delayed to give time for someone to publish a fraud proof and cancel the withdrawal if it's fraudulent. In a ZK rollup, it's very fast. You usually just have to wait for the next batch. The complexity of the technology, for optimistic rollups it's low, whereas for ZK rollups it's high. ZK snarks are very new and mathematically complex. Generalizability is the next one. And for an optimistic rollup it's much easier, because general purpose EVM rollups are already close to mainnet. For ZK proofs it's harder. ZK snarks proving general purpose EVM execution is much harder than proving simple computations. What about per transaction on-chain gas costs? Well, for optimistic rollups, it's higher, whereas for ZK snarks, it's much lower. Because if data in a transaction is only used to verify and not to cause state changes, then this data can be left out. Whereas in an optimistic rollup, it would need to be published in case it needs to be checked in a fraud proof. The last property that we're going to compare is off-chain computation costs, where for an optimistic rollup, it's much lower, though there is more need for many full nodes to redo the computation. For a ZK proof, the off-chain computation costs are higher, because ZK snark proving, especially for general purpose computation, can be expensive, potentially many thousands of times more expensive than running the computation directly. In general, my own view is that the short-term optimistic rollups are likely to win out for general purpose EVM computation, and ZK rollups are likely to win out for simple payments, exchange, and other application-specific use cases. But in the medium to long term, ZK rollups will win out in all use cases as ZK snark technology improves. The anatomy of a fraud proof. The security of an optimistic rollup depends on the idea that if someone publishes an invalid batch into the rollup, anyone else who was keeping up with the chain and detected the fraud can publish a fraud proof, proving to the contract that that batch is invalid and should be reverted. A fraud proof claiming that a batch was invalid would contain the data and the parts of the Merkle tree needed to prove just the specific accounts that were read and or modified by the batch. This data is sufficient to execute the batch and compute the post state root. Note that this is exactly the same way as how stateless clients verify individual blocks. If the computed post state root and the provided post state root in the batch are not the same, then the batch is fraudulent. And inside the original post, there is a Merkle tree that makes this point much clearer. It is guaranteed that if a batch was constructed incorrectly and all previous batches were constructed correctly, then it is possible to create a fraud proof showing the batch was constructed incorrectly. Note the claim about previous batches. If there was more than one invalid batch published to the rollup, then it is best to try to prove the earliest one is invalid. It is also, of course, guaranteed that if a batch was constructed correctly, then it is never possible to create a fraud proof showing that that batch is invalid. How does compression work? A simple Ethereum transaction to send ETH takes around 110 bytes. An ETH transfer on a rollup, however, takes only 12 bytes. And we get that comparison because the bytes for the nonce in Ethereum is around 3, whereas in a rollup it's 0 bytes. The gas price in Ethereum is around 8 bytes, whereas in a rollup it would be 0 to 0.5. Gas in general is 3. In a rollup it's again 0 to 0.5. The 2 parameter is 21 bytes in Ethereum. In a rollup it would be 4. The value parameter is around 9 in Ethereum, whereas in a rollup 3. The signature, 68 bytes in Ethereum, whereas in a rollup it would be only about a half. And the from parameter in Ethereum would be 0, which you recover from the signature, whereas in a rollup it would be 4. So that's how we get the total of 112 bytes on average for an Ethereum transaction, whereas in a rollup it's only 12 bytes. Part of this is simply superior encoding. Ethereum's RLP wastes 1 byte per value on the length of each value, but there are also some very clever compression tricks that are going on. One is the nonce. The purpose of this parameter is to prevent replays. If the current nonce of an account is 5, the next transaction from that account must have nonce 5. But once the transaction is processed, the nonce in the account will have to be incremented to 6, so the transaction cannot be processed again. In the rollup, we can omit the nonce entirely, because we just recover the nonce from the pre-state. If someone tries replaying a transaction with an earlier nonce, the signature would fail to verify, as the signature would be checked against the data that contains the new higher nonce. The gas price. We can allow users to pay with a fixed range of gas prices, for example a choice of 16 consecutive powers of 2. Alternatively, we could have a fixed fee level in each batch, or even move gas payments outside the Rollup protocol entirely and have transactions pay batch creators for inclusion through a channel. What about gas? We could similarly restrict the total gas to a choice of consecutive powers of 2. Alternatively, we could just have a gas limit only at the batch level. What about the to parameter? We can replace the 20-byte address with an index. For example, if an address is the 4527th address added to the tree, we just use the index 4527 to refer to it. We would add a subtree to the state to store the mapping of indices to addresses. The value parameter. We can store value in a scientific notation. In most cases, transfers only need 1 to 3 significant digits. The signature. We can use BLS aggregate signatures, which allow many signatures to be aggregated into a single 32 to 96 byte, depending on protocol, signature. This signature can be checked against the entire set of messages and senders in a batch all at once. The half in the table represents the fact that there is a limit on how many signatures can be combined in an aggregate that can be verified in a single block. And so large batches would need one signature per average of 100 transactions. One important compression trick that is specific to ZK rollups is that if a part of a transaction is only used for verification and is not relevant to computing the state update, then the part can be left off-chain. This cannot be done in an optimistic rollup because that data would still need to be included on-chain in case it needs to be later checked in a fraud proof. Whereas in a ZK rollup, the snark proving correctness of the batch already proves that any data needed for verification was provided. An important example of this is privacy-preserving rollups. In an optimistic rollup, the 500-byte ZK snark used for privacy in each transaction needs to go on-chain, whereas in a ZK rollup, the snark covering the entire batch already leaves no doubt that the inner snark are valid. These compression tricks are key to the scalability of rollups. Without them, rollups would be perhaps only a 10x improvement on the scalability of the base chain, though there are some specific computation-heavy applications where even simple rollups are powerful. Whereas with compression tricks, the scaling factor can go over 100x for almost all applications. Who can submit a batch? There are a number of schools of thought for who can submit a batch in an optimistic or ZK rollup. Generally, everyone agrees that in order to be able to submit a batch, a user must put down a large deposit. If that user ever submits a fraudulent batch, the deposit would be part burned and part given as a reward to the fraud prover. But beyond that, there are many possibilities. 1. Total anarchy. Anyone can submit a batch at any time. This is the simplest approach, but it has some important drawbacks. Particularly, there is a risk that multiple participants will generate and attempt to submit batches in parallel, and only one of those batches can be successfully included. This leads to a larger amount of wasted effort in generating proofs or wasted gas in publishing batches to the chain. 2. A centralized sequencer. There is a single actor, the sequencer, who can submit batches. With an exception for withdrawals, the usual technique is that a user can first submit a withdrawal request, and then if the sequencer does not process that withdrawal in the next batch, then the user can submit a single operation batch themselves. And a sequencer is the most efficient, but it is reliant on a central actor for liveness. 3. A sequencer auction. An auction is held every day or every month to determine who has the right to be the sequencer for the next day. This technique has the advantage that it raises funds which could be distributed by, for example, a DAO. 4. Random selection from the proof of stake set. anyone can deposit ETH, or perhaps the Rollup's own protocol token, into the Rollup contract, and the sequencer of each batch is randomly selected from one of the depositors, with the probability of being selected being proportional to the amount deposited. The main drawback of this technique is that it leads to large amounts of needless capital lockup. And lastly, designated proof-of-stake voting. There is a single sequencer selected with an auction, but if they perform poorly, token holders can vote to kick them out and hold a new auction to replace them. Split batching and state root provision. Some of the rollups being currently developed are using a split batch paradigm, where the action of submitting a batch of layer 2 transactions and the action of submitting a state root are done separately. This has some key advantages. One, you can allow many sequencers in parallel to publish batches in order to improve censorship resistance, without worrying that some batches will be invalid because some other batch got included first. Two, if a state root is fraudulent, you don't need to revert the entire batch. You can revert just the state root and wait for someone to provide a new state root for the same batch. This gives transaction senders a better guarantee that their transactions will not be reverted. So all in all, there is a fairly complex zoo of techniques that are trying to balance between complicated trade-offs involving efficiency, simplicity, censorship resistance, and other goals. It's still too early to say which combination of these ideas work best. Time will tell. How much scaling do rollups give you? On the existing Ethereum chain, the gas limit is 12.5 million, and each byte of data in a transaction costs 16 gas. This means that if a block contains nothing but a single batch, we'll say a ZK rollup is used, spending 500k gas on proof verification, then that batch can have 12 million divided by 16 equals 750,000 bytes of data. As shown above, a rollup for ETH transfers requires only 12 bytes per user operation, meaning that the batch can contain up to 62,500 transactions. At an average block time of 13 seconds, this translates to roughly 4,807 transactions per second, which compares to 45 transactions per second for Ethereum transfers directly on Ethereum itself. And in the post, there is a chart that breaks down the math of this. Now, it is worth keeping in mind that these figures are overly optimistic for a few reasons. Most importantly, a block would almost never just contain one batch, at the very least because there are and will be multiple rollups. Second, deposits and withdrawals will continue to exist. Third, in the short term, usage will be low, and so fixed costs will dominate. But even with these factors taken into account, scalability gains of over 100x are expected to be the norm. Now, what if we want to go above 1,000 to 4,000 transactions per second? Here is where ETH2 data sharding comes in. The sharding proposal opens up a space of 16 megabytes every 12 seconds that can be filled with any data, and the system guarantees consensus on the availability of the data. This data space can be used by rollups. This 1400 bytes per second is a 23 increase on the 60 kilobytes per second of the existing Ethereum chain, and in the long term, the data capacity is expected to grow even further. Hence, rollups that use ETH2 sharding data can collectively process as much as 100,000 transactions per second and even more in the future. What are some not yet fully solved challenges in rollups? While the basic concept of a rollup is now well understood, we are quite certain that they are fundamentally feasible and secure, and multiple rollups have already been deployed to mainnet. There are still many areas of rollup design that have not been well explored, and quite a few challenges in fully bringing large parts of the Ethereum ecosystem onto rollups to take advantage of their scalability. Some key challenges include 1. User and ecosystem onboarding. Not many applications use rollups. Rollups are unfamiliar to users, and few wallets have started integrating rollups. Merchants and charities do not yet accept them for payments. 2. Cross-rollup transactions. Efficiently moving assets and data from one rollup into another without incurring the expense of going through the base layer. 3. Auditing incentives. How to maximize the chance that at least one honest node actually will be fully verifying an optimistic rollup so they can publish a fraud proof if something goes wrong. For small-scale rollups up to a few hundred transactions per second, this is not a significant issue, and one can simply rely on altruism. but for larger scale rollups, more explicit reasoning about this is needed. 4. Exploring the design space in between plasma and rollups. Are there techniques that put some state update relevant data on-chain, but not all of it, and is there anything useful that could come of that? 5. Maximizing security of pre-confirmations. Many rollups provide a notion of pre-confirmation for faster UX, where the sequencer immediately provides a promise that a transaction will be included in the next batch, and the sequencer deposit is destroyed if they break their word. But the economy security of this scheme is limited, because of the possibility of making many promises to very many actors at the same time. Can this mechanism be improved? 6. Improving speed of response to absent sequencers. If the sequencer of a rollup suddenly goes offline, it would be valuable to recover from that situation maximally quickly and cheaply, either quickly and cheaply mass exiting to a different rollup or replacing the sequencer. 7. Efficient zero-knowledge virtual machines. Generating a ZK snark proof that general-purpose EVM code or some different virtual machine that existing smart contracts can be compiled to has been executed correctly and has a given result. Conclusions. Rollups are a powerful new Layer 2 scaling paradigm and are expected to be a cornerstone of Ethereum scale in the short and medium term future. They have seen a large amount of excitement from the Ethereum community because, unlike previous attempts at Layer 2 scaling, they can support general-purpose EVM code, allowing existing applications to easily migrate over. They do this by making a key compromise, not trying to go fully off-chain, but instead leaving a small amount of data per transaction on-chain. There are many kinds of rollups, and many choices in the design space. One can have an optimistic rollup using fraud proofs, or a ZK rollup using validity proofs. The sequencer can be a free-for-all or a centralized actor. Rollups are still an early-stage technology, and development is continuing rapidly, but they work, and some have already been running for months. Expect much more exciting works to come out of the rollup space in the years to come. Okay, and that brings to an end an incomplete guide to rollups by Vitalik Buterin. First, I want to summarize the main points of the article because at times this can get a bit technical. So I want to summarize the main points so that you have those clear in your mind. And then I want to discuss why rollups matter in the Ethereum roadmap, and then go into how I think they'll affect the Eth supply and demand in the near term and long term. So first, just starting out, I am a personal big fan of technical posts. And so I really enjoy when there's a breakdown of the different parameters in what makes the gas price. Because for someone who's non-technical like me, even though I'm learning Solidity now, having that spelled out really makes things much more concrete to see exactly how much of each transaction costs how much gas. And that really helps crystallize why rollups make things so much cheaper. So here's the main takeaway from this article. There are 3 kinds of Layer 2 scaling solutions: channels, plasma, and rollups. Channels in Bitcoin, there's Lightning, that's the most well-known level Layer 2 scaling solution. But for rollups, the main takeaway is that they move computation off-chain, but keep core data on-chain. And this way they solve 2 issues with blockchain scalability, which is the data availability and the computation. To save, quote unquote, space and gas, they post the data to the main chain only every so often. I think the current optimistic rollups in Arbitrum have opted to do this every 6 minutes or so, which will be a proof of stake, a merge kind of epoch. And rollups solve a lot of problems for scale. Now, this doesn't come free, right? There are trade-offs. Rollups, especially today, are very centralized. So Arbitrum, there's only one sequencer. It's the Arbitrum sequencer. And so you're essentially relying on them to do their job properly and to not censor any transaction. The good thing about rollups is that there isn't the honest majority assumption in a rollup. You don't need to reach consensus. The way that the contract is built, you just need one honest node to make a fraud proof. And so even if Arbitrum is running the sequencer, anyone can download a validator node set and point it at the Arbitrum chain and become a fraud-proof watcher. And so making sure that honest transactions are happening is easy, but you won't be able to get transactions through without going through that Arbitrum sequencer. And so it is a much more centralized solution. In fact, one of the kind of the side risks of this happening just happened this past week when a sequencer went offline for I think 9 or 10 hours, and then that was it. The rollup just didn't work. And actually Vitalik talks about this in one of his last points of further research, where what can we do if a sequencer goes offline? And that's just one part of the layer 2 security risks when we go into rollups. There are others around MEV and really maintaining a proper ecosystem of validators that make sure that things are happening properly. But all that being said, I really think that by now, and you should also be convinced by now, that rollups are the future for the Ethereum ecosystem. And I really think it's not only Ethereum, it's any blockchain. And here I'm going to shift from blockchains to traffic and transportation, because in transportation, there's this field called induced demand. And from the field of induced demand, we can learn really that there is no such thing as a blockchain that will be successful, that will have space left on the core blockchain. And basically, if you think about it this way, it'll make much more sense. There's a main highway between two roads, let's say between New York and Washington, D.C. Let's say there's only one highway. And as long as a lot of people want to make that trip between New York and Washington, D.C., that's going to be a clogged highway because the trip is worthwhile and that's the only way to go. Now, what happens is that as that trip becomes clogged, let's say it's a 4-hour drive, and then with traffic, it becomes a 12-hour drive. Basically, traffic clogs up the road. And then the authorities say, well, you know what, there's a lot of traffic, let's build a side road, or let's add a lane to the highway. And so they add a lane to the highway and magic happens. Traffic drops from 12 hours, it goes back down to 4 hours because they've added 1 lane or 2 lanes. And then what happens is that everyone says, hey, it's 4 hours to drive from New York to Washington, D.C. on this one great highway. Let's go. Let's buy a car and let's start working in Washington. And people start making that commute again. And even though you went from 4 lanes to 6 lanes, over time, you're just going to go back to that 12-hour traffic jam. Now, I just gave a pretty bad example between 2 really distant cities, but the point remains the same. Induced demand basically means that when you make the transit easier, you are just going to cause more people to hop in their car, buy a car, and get on the road. And so adding lanes actually never reduces traffic in the long term. The only way to do that is by getting people on the subway or the bus, basically mass transit. And the same is true for blockchains. If you have a blockchain that is in high demand for any reason, whether it's Bitcoin because it's ultrasound and kind of secure money, or Ethereum because it's ultrasound and secure computation, and people want to be using that block space, then the blocks on the original block space will just fill up and the gas will increase. And the only way to do that is not by increasing the block size, because that will just create more induced demand and that will also fill up. It's by getting people in mass transit, in subways and in buses. And rollups are a form of mass transit. And the thing is, we think that great, we'll have 1 rollup, 2 rollups, and the congestion will clear. But no, what happens is that as congestion clears, as transactions become faster, as the gas price drops, that will induce a new wave of demand, new kinds of applications that just aren't able to run today on the main net because gas prices are too high or transaction speed is too low. But once you have the ability to do that, that will create new demand. We're already seeing that today on Arbitrum or on Immutable X or Polygon, and all of those enable new kinds of transactions and new induced demand. And so we think today that where we are is good, but in the future, I can easily see hundreds and hundreds of rollups, each one doing their own thing, each layer 2 specializing in a different area. A game could have a rollup, a community could have a rollup. Every kind of niche application will have a rollup because at the end of the day, where you have demand for a scarce product, the only way to get around it is by getting people on the subway. And that's why I think the monolithic approach to a blockchain, where a blockchain does it all, just won't last. And you have to have a modular kind of blockchain. We've spoken about this in our second episode, ultra scalable Ethereum. The main point there was that you need to have a modular blockchain where you're managing consensus as one part, computation another, and data availability as a third. And all of those together form the modular blockchain. Now, when it comes to kind of ETH supply and demand, well, what happens near term as we migrate from the mainnet to layer 2s is that overall, the amount of ETH that gets burned in transactions will decrease. And I'm saying this with a little asterisk because what happens is if I wanted to do a transfer on Uniswap, on the mainnet, let's say that would cost me $180 of ETH. And I go over to do that on Arbitrum or on Optimism or on Polygon. Over there, it's much, 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 much lower. Right? On Polygon, I can do swaps today for, $0.50, and that's an exaggeration. And so the ETH that's getting burned by, EIP 1559 actually shrinks because the batches that I would have once done on the mainnet, I'm now doing on a much cheaper layer 2. And so in theory, what you have is you're taking fees away from the Ethereum ecosystem. And so you have less burn. But, and this is a big but, I'm making many, many more transactions today than I would have ever done on the mainnet because of the lower fees. And so that's already kind of a counterbalancing effect. And the idea here is if you go back to the induced demand, what happens is that short term, when you add in an extra lane to a highway, yes, you have lower traffic. You have shorter time stuck in traffic for a while, but then over the following months, years, however long it takes, traffic rises up again. And at the end of the day, you have more cars, you have more transactions. And I think the same thing is going to happen with Ethereum. We're going to have a short-term dip as people migrate over from mainnet to layer 2s, and the ETH gas gets reduced because of that. And then you're going to have this long-term humongous growth as the induced demand comes and kicks in. Now, I added an asterisk, and that's because, well, in crypto, who the hell knows what's about to go on, what's going to happen. And the asterisk is basically, there can be so much demand for the base layer of Ethereum that kind of dip before the growth might never happen. There might be enough applications, enough users who just want to operate on the mainnet that the gas fee never drops significantly, and everything that happens on layer 2s is just a net positive. And just an example to bring that home is that I could be buying NFTs on mainnet and not transferring them over to a level 2, but on level 2 I'm going to be playing a game, and I'm going to be burning ETH there. Now it'll be a small amount of ETH because it's on layer 2 and the transaction fees are much lower, but I would never be doing that on the mainnet. And so that's a net added bonus, and the mainnet is still congested with traffic because, Bored Apes are worth a bazillion ETH. And so we never lose that burn. And that could also easily happen. Who knows? This is crypto. But those are kind of the two ways I'm thinking about how rollups affect the supply-demand dynamics of ETH. I hope this read-through and the summary were really beneficial in understanding kind of the ins and outs of rollups. It's a bit technical at times, but it's really important to understand because rollups are the future of a lot of what's going on in Ethereum scaling. And so it's important to understand what they are and the different trade-offs that they come with and which kinds of rollups are out there.